All right, so we'll finish up section 6.2 today. Tomorrow we'll review the first half of class, and in the second half of class we will start the test, and then Friday we'll finish up the test. Okay, so two things we're going to look at. First thing is we're going to finish off unit circle trig by looking at how can we find all 6 trig functions for angles that are 30, 60, 90, 30, 60, 45, and multiples of those. So multiples of 45 would be like 45, 90 you already know how to do, 135, 180, that one you know, 225, 270, and 315. Okay, and then obviously some overlap here. Multiples of 30 would include 30, 60, 90, which again, that one you already know. All right. So we'll look at that first. And then we're going to start to look at trig identities. Okay, and again, that's a topic we'll spend a couple weeks on, so just kind of a real quick introduction to that. All right. So first thing I want to do is just kind of remind what we're looking at here. So we have a unit circle. Okay, what's the radius in a unit circle? Yeah? 1. And yesterday we looked at the quadrantal angles. Okay, the 0, 90, 180, 270. Right. So we're going to start today by looking at a 45-degree angle. Okay, so if you draw that in standard position, initial side is on the positive x-axis. Terminal side should be halfway between 0 and 90. Okay, so any questions on that? So now what I'm going to do out of that angle is I'm going to create a triangle. Okay, the way I'm going to create a triangle is by drawing a line straight down, perpendicular to the base, or perpendicular to the initial side. Okay. So what we just created there is a 45, 45, 90 triangle. This angle is 45 because that's the angle of elevation from the initial side to the hypotenuse. And if all the angles add up to 180, the other one has to be 45 as well. Okay, so basically our goal is to figure out how long is this side, that's x, and how long is this side, that's y. If you can figure out the length of those two sides, that tells you how far to move from the origin to the right, that's your x, and then from that spot up to the top of the triangle. That's your height, that's your y. Now, normally we just did a problem, so I think you probably already know what x and y are, but let's pretend we don't know them, but we should know something if you compare them to each other. What would be the connection between x and y if you compare them to each other? Yeah?
They're equal.
Yeah, they're equal, because that's an isosceles triangle, so they're the same. So once we find one, we will know the other. Okay, so I just drew the same triangle a little bit bigger. Is there any side in that triangle that I already know the length of? Yep. How long is that? 1, because that's the radius in the unit circle. Now, I labeled the other two sides x and y because if you were just making a diagram, you wouldn't know beforehand that they're the same. But now that I know they're the same, we could call each side the same thing. Right, so I'll just call this, let's call it T and T. I didn't use x and y because I didn't want to confuse it with the coordinate. But just a generic isosceles triangle, just use any two letters that are the same. And now, how could you solve for T there? What theorem could you use that involves the sides in a right triangle? Leo?
Pythagorean theorem.
Yeah. Can you plug in what I have here into the Pythagorean theorem?
2t squared equals 1.
Yeah. We have t squared plus t squared equals 1 squared. And it'll simplify to what Leo just said. All right, so where were we? Yeah, simplify what Leo had said. So 2t squared equals 1. Next step would be to do what? Yep, Sam? Okay, you could. We could do that first. So you'd have the square root of 2 times t equals 1. All right, now what? Still have to get t by itself. So Gracie, what would my last step be?
Well, you would square root of 2.
Yep, we got that. So we've got the square root of 2.
Would you divide by the square root of 2?
Yeah, we divide by the square root of 2. Exactly. Divide by the square root of 2, square root of 2. And there's your answer for t. It's 1 over the square root of 2. The only problem is we just can't leave the square root in the bottom. So if you fix that, what would you get for an answer for t? Leo?
Square root of 2 over 2.
You get square root of 2 over 2. So now we know the bottom side is square root of 2 over 2, and the height is also square root of 2 over 2. If you're wondering what that is as a decimal, it's about 0.707. So a little less than 1. All right. So now we've got those two numbers. Let's go back up. So that means we can now fill in the coordinates for 45 degrees because we know what x and y are. Okay. Shauna, x and y are both the same number here, and they are both what number? Yep, root 2 over 2, comma, root 2 over 2. So that's always the coordinate for 45 degrees, and that will never change. Okay. Any questions on how we get the coordinate for 45? Okay, let's look at doing the coordinate for 30, 60, 90. Okay, we'll do the same thing again. Pretend that this was inside a unit circle. Okay, kind of like that. This would be the center of my circle. Kind of goes off the page. Is there any side in that triangle that I already know the length of? Yeah.
The hypotenuse is 1.
Yeah, the hypotenuse is 1. Now that doesn't really help me well, it indirectly helps me, but what I really want to know is the base and the height. So let's label them just like we did before. Now, can we say that x and y are the same like we did last time? Okay? No. That's a scalene triangle, so they're different. So if you try the Pythagorean Theorem, this is what you're going to get. It's not really helpful. You get 1 squared equals x squared plus y squared. That's basically the equation of a circle with radius 1. It's the general form of the equation of a circle is x squared plus y squared equals r squared. So that doesn't really help us because there's 2 variables. So we have to figure out one of these variables first. Does anyone have a guess at how we could figure out one of these variables? Without using any tricks, like if you know a 30, 60, 90 right triangle, you know the relationship between the short leg and the hypotenuse. There's a connection there. Does anybody know how to do it without using any tricks? It's a little, it's kind of tricky to come up with, yeah.
Could you use like sine and cosine?
Okay, if you knew right triangle trig, yes, you could use sine and cosine, absolutely. But let's pretend we don't know that either. I'll give you a hint. I'm going to start just by taking this triangle and making a copy of it. Okay? Does that help? Let me do something with that copy. I want to somehow do something to that copy, and then put it with the original triangle to make something. And I usually get one of two guesses. We'll see which one comes up. Yep.
You can make a rectangle.
I could make a rectangle. We just kind of flip it around like that, I guess. But what would I do with that now? All I really know there is that the side on the left is the same as the side on the right, and the side on the top is the same as the side on the bottom. But I still don't know what the top and bottom are, or what the left and right are. There's something else I could do. Yep, Juliana?
Like, would you make another triangle, like a bigger one?
Yes, I want to make a bigger
So
triangle.
you like flip it and then have the y's match up.
Okay, so you're thinking flipping it this way, like that?
What's
make-
the other way?
It's the other way.
The other way? Yeah, when you do the back, like X side.
So let's make the x sides match up. Okay. And now, what kind of triangle do I have there? Yeah?
Equilateral.
Equilateral, right? Because this is 30, that's 90, that's 60. 60, 60, 60. So what do we know in an equilateral triangle?
Equals.
What's that?
All equal sides.
Right, all the sides are equal. So if this side is 1, this side is 1, and this entire side is 1. All right, so now what? Yeah.
So now we can know that y equals 1/2.
Yeah, y is a half because we made a copy, so we know these two sides are congruent. So basically, if that side is y plus itself, because you're adding another copy of it, equals 1, so y would have to equal 1/2. Okay. So now I can erase the bottom part of that triangle. I don't need it anymore. Or I can keep it, but I'm just going to move it away so we can now focus on the original. Okay. And I'm going to erase y and make it 1/2. All right, so now I can use Pythagorean Theorem. Very easy, and solve for x. So we get 1 squared. Actually, I'll just do it out as we go. 1 squared is 1. 1/2 squared is 1/4. Plus x squared. If I bring the 1/4 to the other side, what will that give me on the left? Yep. 3/4. And my last step to get x by itself would be, yep,
Square root it.
take the square root. So when you square root a fraction, you square root the top, square root the bottom separate. This time the bottom has a nice square root because it's a perfect square, so I don't have to fix it. So there's my x value. Square root 3 over 2. Okay. So again, if this was on our circle, 30-degree angle, can somebody give me what the coordinate would be? I just need a little more space over here. What would the coordinate be for 30 degrees?
It would be the. Oh, it would be the square root 3 over 2.
And then 1/2. So there's your coordinate for 30. Right, and now if we had, let me just put in where the y-axis would be on this circle. Right about there. So 90 would be straight up. 60 would be a little bit before 90. So I'm going to make my triangle here. What's the connection between the triangle I just drew and the one I had originally? Yeah.
It would have the same coordinate, but the x and y would be flipped.
Yeah, they're congruent triangles. The only difference is you've taken the 30, 60, 90 now and kind of stood it on its base and kind of reflected it. So now the 60 is at the bottom and the 30 would be at the top. I'm not going to label the 60 because I think it Maybe if I did it in a separate color. So that's the 60. What's in red. Right, so now the coordinate is just going to flip the x and the y. So for 60 degrees, your coordinate is root 3 over 2, 1/2 root 3 over 2. And if you forget which way is which, well, if you take the square root of 3 and divide by 2 on your calculator, it's about 0.866. That's bigger than 1/2. 1/2 is 0.5. So in a 30, 60, 90, the longer leg is the bigger number, 0.866. The short leg is the smaller number, 1/2. So if you ask me about any angle that's a multiple of 30, I try to picture that triangle in my head, and which way would the long side go? If the long side is x, then x is root 3 over 2. If the long side is y, then the y is the root 3 over 2. And the short side is the 1/2. So knowing those two coordinates, along with the 45, 45, 90, will allow us to figure out any trig function that's a multiple of 30 or 45. So we'll start in the first quadrant, but then we'll look at some of the other quadrants. Okay, so let's find the 6 trig functions of 45 degrees. Okay, what do we have to know first if you want to find the trig functions of any angle? Yep, Gracie. You've got to know the coordinate. So here is where it's helpful if we have the coordinate memorized, we don't have to go through and figure it out again. What's the coordinate for 45 degrees? Yeah.
Square root of 2 over 2. Square root of 2 over 2.
Yeah. And now that should look familiar. You did that in the homework. That's the, I think someone asked me about that question. So we didn't know that it was a 45-degree angle, or I didn't know what it was, but you didn't need to know last night. You had the coordinate already. Today, you have to know how to find the coordinate yourself. Okay, so let's go through the 6 trig functions. Shauna, what would the sine be?
Square root of 2 over 2.
And which one did you pick, just so we know? Sine is y. Yep, sine is y. Dylan, what about the cosine?
Square root of 2 over 2.
Square root of 2 over 2. That's the x. And Gracie, the tangent?
It would be
1.
1.
If you want to do the cotangent, just because that one's quick, when you flip it, it's also 1. Jay, what's the connection between sine and cosecant? Like, what do you do to one to get the other?
Just flip it.
Flip it. Okay, so just take what you have and flip it. Do you remember what you get if you flip root 2 over 2?
Just square root of 2.
It was just square root of 2. If you flip it, the root goes to the bottom, and then when you fix it, the 2's cancel. So Megan, what about the secant of 45?
It's the same thing.
Same thing. So there's your 6 trig functions for 45 degrees. Any questions on that? Right, so let's look at 30. So if you can, try to think in your head, visualize a triangle for the 30 degrees and figure out where the long side is and where the short side is. Right, for a 30, 60, 90 triangle, and we're dealing with the 30-degree angle near the origin, which side is the long side? Would that be the base, which is the x, or would it be the height, which is the y? Which side is the long side? The base. If you need to sketch it, just make a rough sketch. There's 30. Here's your triangle. If you sketch it reasonably accurate, it's pretty clear to tell that the base is the long side and the height is the short side. Okay. So x is the long side, and how long is the long side? What's the number for that? Yeah. So x is root 3 over 2. Y is the short side. And how long is the short side? Well, yep, Liam. 1/2. Okay, so there's your coordinate. Now just fill in all the values. Okay. Going forward, it's more important that you can just figure out that coordinate in your head, right? Because if you can do that, then you'll be able to figure out all these trig functions. That's just arithmetic, and eventually you'll probably even have them memorized because they come up a lot. But let's go through it and see where we're at. So sine of 30, Sam, what would that be?
Like that.
Yeah, and we'll always just leave it as a fraction, but yeah, 1/2. Juliette, cosine of 30?
The square root of 3 over 2.
Square root of 3 over 2. And now the tangent is when you divide the sine by the cosine, the y over x. So I just imagine putting a fraction bar in there. If you divide those two fractions, what would cancel out? Megan? The 2's. Because if you divide a fraction by a fraction, you take the bottom one, you flip it, and multiply by the reciprocal, right? So the 2's would cancel out. So you'd have 1 divided by square root of 3. But we need to fix that because the root's in the bottom. So what would you get if you multiply top and bottom by square root of 3? Yep, Sam. Square root of 3 over 3. Now keep that other answer that it was equal to, because that's going to come in handy in a second when we do cotangent. Okay. In fact, let's do that one right now. So you have two choices of what you could flip. You could flip 1 over square root of 3, or you could flip root 3 over 3. Which one is quicker to flip? How come?
Because it's already, if you flip it, there will be no square root at the bottom.
Yeah, if you flip it, you get the final answer because the root's in the top. If you flip the other one that we circled, the root's going to go back to the bottom, and if you fix it, you would get that as the final answer. How about cosecant? Trevor, what's my cosecant?
2 over the square root. Oh, secant, never mind. 2.
2. And my secant is 2 over the square root of 3. And can anyone tell me what that would be when you fix it? So there's no root in the bottom. Yeah.
2 over 3.
Well, the square root has to stay somewhere. We can get rid of it from the bottom, but then it's going to end up in the top. Leo?
2 square root of 3 over 3.
Yes, 2 square roots of 3 over 3. Okay, any question on that? So you had the 2 over 3 part where we just lost the square root. Yeah. So there's your 6 trig functions of 30. Okay, let's look at this one. 6 trig functions of pi over 3. Okay, so if it's helpful, you can think in your head pi over 3 in degrees. What's pi over 3 in degrees? Yep. 60. So I want the coordinates for 60. Well, if you know 30 is root 3 over 2, 1/2, 60 is switched. So you're going to get all the same answers here that you just got on the last problem, but they're going to switch places. Okay, so we'll put both of them up in a minute after we get all the answers and compare them. Tessa, what's the sine of pi over 3? Yep, square root of 3 over 2. Okay, Rebecca, the cosine? 1/2. And the tangent is when you divide the sine and the cosine, divide the y and the x, the 2's cancel, you just get the square root of 3. Secant, could do that one quick because there's no root. Even ones with roots you should be able to do reasonably quickly because we just had all these answers on the other page. What about the cosecant of pi over 3?
2 times the square root of 3 over 3.
2 times the square root of 3 over 3. Okay. And what about the cotangent? Yeah. Square root of 3 over 3. Now, let's see the pattern on how things switch places. So, the sine flipped with the cosine. The secant flipped with the cosecant. And the tangent flipped with the cotangent. Okay, those are called cofunctions, the way that I just grouped them. Sine, cosine, secant, cosecant, tangent, cotangent. We normally think of the relationship as going across, and that is another one, that's the reciprocal, but that grouping is cofunctions. Those are the ones that switch places. Okay. Any questions on that? All right, so let's take a look at the 6 trig functions of 135. So if I asked you to do unit circle trig, the angle that I give you has to be a multiple of 45 or 30. But you have to figure out, based on the number, is it a multiple of 45 or 30? So what's 135? What's that a multiple of? Yeah, that's a multiple of 45. So let's figure out roughly where it would be. Okay. Where's 135? Yeah.
It's like the middle of 180.
Yeah, it's exactly halfway between 180 and 90. So you just created a triangle, and because that 135 is a multiple of 45, the triangle you created is a 45, 45, 90 right triangle. If you're not sure, another way you can think about it is the distance from here to here is 45. 90 plus 45 is 135. So if this arc is 45 degrees, and so is that angle, that's a theorem from geometry. Well, if that's a 45, then that also has to be a 45 because the quadrant itself, the axes make a 90. Okay, so there's different ways you can think about it. Okay, so we have a 45, 45, 90. How long is each side in the 45, 45, 90? Yeah?
Square root of 2 over 2.
They're both square root of 2 over 2. But when we write the coordinate, we have to be careful about the sign now, because now we're in a different quadrant. That's the only thing that changes when you go into another quadrant. Okay, so what would be the coordinates for 135? Yeah?
Would it be negative square root of 2 over 2? And then the next one would be square root of 2 over 2.
Yeah. So there's 4 versions of the 45-degree angle coordinate. Both positive, both negative, and then one of each where you have one negative and the other positive. All right, so now the sine is root 2 over 2. The cosine, negative root 2 over 2. And what about the tangent? Yeah. Negative 1. Okay, I didn't have you find all 6 here because we've done this coordinate quite a bit, but you would just flip them. So you get root 2, negative 1 if you flip them. Any questions on the 6 trig functions of 135? All right. 6 trig functions, actually this one we'll just do 3. 7 pi over 6. First thing we might want to do is change to degrees. So to change to degrees quickly, think in your head, what's pi over 6? And then multiply it by 7. So what's 7 pi over 6? We have
210.
210. Right. Pi over 6 is 30. 30 times 7, 210. Now before I even sketch it, I'm going to start thinking, is that a multiple of 30 or 45? Sam? 30. And this is the sketch that after a while, hopefully you can just kind of visualize in your head. Here's 180. 210 is just a little bit past it. Okay, so draw your triangle. So the long side, is that on the x-axis or the y-axis? Yeah. The x-axis. And how long is the long side in a 30, 60, 90? Time? How long is the long side?
Square root of 3 over 2.
Yep. And the short side? 1/2. Okay. So now I've got my sides labeled correctly. Now for the coordinate, just take into account the directions. So what would be the coordinate for 210 degrees? Juliana?
Negative square root of 3 over 2.
Yep.
And
Negative
negative 1/2.
1/2. Okay, so Abby, what would my sine be? Negative 1/2. Cosine? Negative root 3 over 2. And what about my tangent? Yeah,
Negative square root of 3. Oh no, it would be positive square root.
it would definitely be positive, and it's still going to be a fraction though. Yeah? Yeah, so you had the positive, and you had the square root of 3, but it's also divided by 3. So you get 1 over the square root of 3, and then when you fix it, root 3 over 3. Okay. Any questions on that one? So all the angles you should be able to do, there's 16 of them. There's the 30, the 45, and the 60 in every quadrant. So there's 12. And then there's the 0, 90, 180, 270. There's 4 more. So there's 16 different angles I could ask you about. And for each angle, I could ask you for one of the 6 trig functions. Okay, what if you had something like 570, and I asked you to find the trig functions of that? What would you want to do first with it? Yep.
Subtract 360.
You would subtract 360 to find an angle that's, what's the word? 570 and 210 are coterminal. Now, the problem I just said, 560, is actually the problem we just did. Same thing if you had a negative angle. If you had a negative, add 360 to make it positive first. Okay, so unit circle trig works great as long as you're dealing with angles that are multiples of 30 or 45. And actually, once we learn some more advanced trig identities, we can even do the multiples of 15, knowing the 30s and the 45s. But for now, if you have an angle that's not a multiple of 30 or 45, we're going to use the calculator. Okay, so the first one says, find the 6 trig functions of 42 degrees. Well, first thing is make sure you look at the angle and look at how the angle is being measured. This one is in degrees. So I'm going to take my calculator, and to change between radians and degrees, you press mode. right at the top. Under mode, if you go down to the fourth row, use the arrow to put it on degrees, hit enter, and it should change the word up at the top to degrees. All right. And now you just type it in. Let's start with the sine, the cosine, and the tangent. So sine of 42, cosine of 42, tangent of 42. Hey, if you got those answers, then you're doing it right. Okay, how many people got those answers? Okay. But now the other three it's asking for is the secant, the cosecant, the secant, and the cotangent. Do you have buttons for those three on the calculator? No. There's no button for that. There's this sine to the -1, cosine -1. That's something different we'll talk about later on. That's inverse trig. But let's use the same way we've been doing it all along. Once you get the three on the left, what do you do with each one of them to get the three on the right? Yeah, you flip them. So instead of typing in sine of 42, I'm going to type 1 over the sine of 42. That's my cosecant. 1 divided by cosine 42. That's my secant. 1 divided by tangent 42. That's my cotangent. Okay, so that's the only way to type in the other three on the calculator. You have to do one, you have to flip it, 1 over. Notice on the ones on the right, I put the parenthesis after the 42 to close the argument to the tangent function. It's not really important if you close it because there's nothing coming after it. If you were going to then do +6 to it, there's a big difference between this and that. That's going to take the sine of 42, get the answer, and then add 6. That is going to treat it like that. It's going to do the sine of 48. So unless you have something coming after it, it's not really important to close it. At least for calculations. Okay. Any questions on that? All right, so that pretty much finishes up the unit circle part, but that kind of ties in with the next part, this idea of having to flip a trig function to get another one. It doesn't just work for 42. You could do it with 57, 106. You could do it with any number you want. So if a formula works all of the time for any number that you want, then that's called an identity. Okay, so in the problem we just did, we had to use what was called the reciprocal identity to get the cosecant, the secant, and the cotangent. Okay, we used the three identities on the left. Flip the sine to get the cosecant, flip the cosine to get the secant, flip the tangent to get the cotangent. Now, if you flip it again, you could go back to what you started with. If you flip the cosecant, you get sine. If you flip the secant, cosine. And if you flip the cotangent, you get tangent. So technically, the three on the left are the identities. The three on the right are just a different way of writing the ones on the left. If you call these 6 different identities, then that's kind of like saying this and this are different formulas. Not really. They're just the same formula written a different way. So the top row is the same formula written different ways. Same with the middle row, same with the bottom row. Okay. and leave a little bit of space, maybe however much space you just used for that, leave that much more below it, because I'm going to give you, in a minute, I'm going to give you some more identities, and it's kind of good to have them all in the same spot. So leave a good amount of space below that. Okay, so those are the reciprocal identities. Okay, you know what? Actually, maybe let me give you. Let me give you all the identities now, and then we'll go back. So you have the reciprocal. Here's the tangent and the cotangent. We already talked about this one. Okay, we said that sine divided by cosine is tangent, y over x. So if you had a calculator where the tangent button was broken, and you had to figure out the tangent of something, you could take the sine of that and divide it by the cosine, and it would come out as the tangent. And if you flip it, well, that's the reciprocal. It's the cotangent. Okay, so today we'll do a couple quick problems with the tangent and cotangent and reciprocal identities. The last group of identities, it's kind of out of the fundamental, the real basic identities. This is the last group. We're not doing anything with them for this test. But just so you have them all in the same spot, I'll give them to you now. Okay, so if you ask somebody what would be considered the fundamental identities in trig, they would probably say the reciprocal ones, the Pythagorean ones, and maybe the tangent and cotangent. Those are also called quotient identities. Okay, but don't worry about the Pythagorean identities today. And if you want to make yourself a little note, like, well, what is an identity again? Because I described it. It's a formula that is always true. Okay, I have a thing written right here. So an identity is an equation that is always true. If you already know that, you don't really need to write that. But if you wanted to put kind of a heading on the page of notes for all those things you just wrote, those are the fundamental trig identities. Hey, you've seen identities before, okay, in Algebra 1. If I gave that problem to somebody in Algebra 1 and said to solve it, that equation is an identity. You have exactly the same thing on the left and on the right. So you could pick any number you want for x and make that equation true. 2, 3, 7, 12 and a half. It's an identity. So we're not talking about algebraic identities. We're getting into trig identities. There's a connection with algebra. Hey, any question on that? All right. You know what? For now, we don't have to worry about this. We'll talk more about that. This idea we've already talked about. The idea that you can add or subtract 360 or 2 pi to any angle in trig. So I just didn't formally give that a name. It's called the periodic property. That's kind of separate from trig identities, but that's a property we've been using. So if I wanted you to take, actually let's do it on here, the sine of, I don't know, 400. Well, you can do it that way, or you could just take the sine of 40. It's the same thing. I subtracted 360. So adding and subtracting multiples of 360 2 pi times 1, 2 pi times 2, any number of multiples you want will always result in the same answer. And that's called the periodic property. Periodic means repeating. All right. So let's look at type of problem in identities. We get all that. So let's look at this. Cosecant times tangent. So the goal is I want to simplify that. Because if I had to do something with that in calculus, it would be a lot easier if it wasn't 2 trig functions, but if I could just make it 1. So the trick, and this doesn't always work, but it will in this problem, is to change everything to sine and cosine. If you already have a sine and cosine, leave it. If you don't, change it. So let's look at cosecant. So basically, using substitution, can somebody tell me another way to write cosecant using one of the formulas I just told you? Yeah?
Cosine over sine.
That would be cotangent. It would also be the way you would have to type in cosecant on the calculator because you don't have a button for it. Yep?
1 over sine.
It's 1 over sine. And sine of what? Like, what are we taking the sine of? The sine of anything. I just put theta. It's a variable. Could be sine of 12, sine of 15. It doesn't matter. Now, how about tangent? What's another way I can write tangent? But I want to use sines and cosines. So we have a couple ways we can write tangent, but sines and cosines. Juliana? Okay?
Sine over cosine.
Yeah. Sine over cosine. Now, you're going to multiply those two fractions together. That's just like multiplying 1 over 2 times 2 over 5. What's going to happen if you multiply straight across?
The signs are going to cancel.
The signs are going to cancel out. So you're left with 1 in the top. You're left with cosine in the bottom. And 1 divided by cosine is something we can simplify even more, and we won't have a fraction. Yep, Sam? Secant, yes. So, if you had to do something with the cosecant times the tangent in calculus, you could just say, well, instead of that, I'm just going to work with the secant, and it's exactly the same thing. Much simpler. There's no product, and it's only 1 trig function instead of 2. Any questions on that one? Let's try this one. Secant times cosecant. And we'll try the same trick. Change to sines and cosines. Anybody tell me how I can rewrite secant? Abby?
1 over cosine.
1 over cosine. And cosine, well, the only thing you could do with it if you want is make it a fraction. What do you get if you multiply those together? 1. Which, if you look at it right away, secant and cosecant are reciprocals of each other. Anytime you take something and multiply by its reciprocal, doesn't matter what it is, you always get 1. Question on that one? Let's look at this one. Let's say I had sine squared over cosine squared. What does sine squared mean? And I should put my argument in there. does it mean to take sine and square it? About the same. Well, pretend it said x squared. What does it mean to take x and square it?
You're multiplying sine times sine.
Yeah, you're just multiplying it by itself. Sine times sine. And in the bottom, cosine times cosine. Now, look at that. I know it's one big fraction, but pretend it was 2, which you could write sine over cosine times sine over cosine. What's sine divided by cosine? That turns into something. Yeah? Tangent. Times sine over cosine again is tangent. What's tangent times tangent? Yeah.
Tan squared.
Tan squared. So we knew from the identity, sine over cosine is tangent. Well, sine squared over cosine squared is tangent squared. So based off that idea, what do you think sine to the 4th over cosine to the 4th would be? Without doing the whole thing out.
Tangent to the fourth.
It would be tangent to the 4th. Okay, so kind of the point I'm trying to show you with that one is that you can use identities with higher powers. If 1 over sine is the cosecant, then 1 over sine squared is the cosecant squared. 1 over sine cubed is the cosecant cubed. I didn't show it to you with a reciprocal, I showed it to you with the sine over cosine. Okay, but you can use those basic identities with higher powers. Not the Pythagorean. I did not write Pythagorean there. Okay, in the Pythagorean, it then said sine squared plus cosine squared equals 1. You cannot say sine cubed plus cosine cubed equals 1. No. Only the reciprocal, tangent, and cotangent. A lot of times the exponents don't get that high, but technically it could go as high as you want. Hey, any questions on that? Okay, so homework tonight, it's on 335. It's 13 through 17. 21 to 25, 29 to 32, 37 to 40, 45 to 47, and 50, 55, 56. Okay, there's one problem I put here that's not in the book, and I'd like you to try to simplify secant squared divided by tangent squared. And my hint would be change everything to sines and cosines, and you'll probably get some stuff that cancels out. Okay. On the test, there'll be one problem with trig identity. Okay, just one question.